The stream has begun. All right. So we are going to start today, I decided, with example 4, because going through the process of actually fitting these models with data will allow us to review some of the concepts. So all of the data that I have for examples in this class is real data, which means unfortunately I can't give it to you to play with, but it does mean that it's not going to be perfect data like you would see in the textbooks. That's one of the things that always drives me nuts when you read a textbook and everything works exactly like it's supposed to and all the assumptions are met and it's beautiful and wonderful and it's like, yeah, that's never going to happen in my life. So let me tell you about the background of this project. So I'm going to give you some analyses based on a publication that was finally published in 2005. And I say finally because it took many, many years to get to that point. This is from a graduate research assistantship that I held for 25% time while I was a graduate student at the University of Kansas from would have been 2000 to 2002-ish. I'm trying to do my timetable. Yes, so 2005 is when it was finally published. So this paper, the first author of it is a close friend of mine. She is no longer in academia. The second author of this paper was her advisor, who is dead, and I am third. And that means that I get at least one email a week of people asking me if they can use the Heartland Forgiveness Scale in their research because I'm the only author who is able to be found. So let me just put it out there to all of YouTube. Yes, you can use the Heartland Forgiveness Scale in your research. It is publicly available. The items are published in this document. You do not need my permission. Knock yourself out. There is a website for the Heartland Forgiveness Scale because there are dozens of translations into other languages of this thing. So little did I know that a job that I took just for the sake of having a little bit of extra money in graduate school would turn into a thing. This is by far my most cited publication, the Heartland Forgiveness Scale. And getting this scale published was somewhat problematic because there are 3 different domains of forgiveness that the authors wanted to measure. One of them is the ability to forgive yourself. Another is the ability to forgive other people who have harmed you. And the third one, which is the most controversial, is the ability to forgive situations. And reviewers did not like that. You can't forgive a situation. I reject your paper. I don't think so. Yes, you can. It's the ability to get past shit that happens to you that's no one's fault, right? That's what it means to forgive a situation. Of course, I couldn't put that in the paper, but that's my loose translation. So I picked the situation subscale of this just as a final to reviewer 3 into along the way who tried to block publication because they didn't believe you could forgive a situation. Yes, you can. And we're about to. So these are real data. Here are the 6 items that we're going to be analyzing. And these items are measured in 1,100 college students, because this is from psychology and that's how we do research, is to collect data on college students. And the response anchors are 7 options, ranging from almost always false of me up to almost always true of me. And 2 of the response, actually 3 of the response options were not actually labeled. So the reason that I joined this project is because when they initially submitted things for publication, they had done what they thought was an exploratory factor analysis. And the reviewers all came back and said, no, we want a confirmatory factor analysis. And they said, we don't know how to do that. And so they put an ad in the Kansan, the paper, and then I got a job because I know how to do that. It turns out that they did not actually do an exploratory factor analysis because they used the default procedure in SPSS under factor, which is a principal components analysis with Varimax rotation. So spoiler alert, the factor analysis didn't work like it was supposed to. Spoiler alert. You will find this when you play with your real data as well, but it does make for a good example because it is real data and it isn't going to cooperate perfectly. So right off the bat, I can point out the major reason why things didn't quite work out the way they were supposed to, and that is because 3 of these items are reverse coded. They are worded to talk about holding grudges rather than being forgiving. So when things go wrong for reasons that can't be controlled, I get stuck in negative thoughts. I continue to think negatively. It's really hard for me to accept negative situations. So that is the opposite of forgiveness. And the authors deliberately created the scale to have 3 indicators of each of their constructs, self, other, and situations that were positive, and 3 that were negative. And so we were eventually able to do something about that. And so this will show up again in a later example on higher order factors and method factors, but for now we're just focusing on these 6 items. So first thing always you can do, stare at a correlation matrix. Do you remember what I told you about staring at a correlation matrix? If your indicators are not correlated, what does that mean? I'll take words, gestures, head shaking. SOL, that is correct, Kelly. SOL means shit out of luck. Game over is it? Yes, that is my preferred phrase on this one. Game over if the indicators are not correlated. Because the whole point of the latent factor is to be able to anticipate the pattern of correlation as consistent with measuring one thing versus 2 things versus 3 things. So this is each pattern points towards a particular dimensionality. And if there's no correlations, there's no potential for a pattern, there's no point. So we do have correlations, and I've highlighted, though, the particular pattern that's going to cause problems with the factor structure. The items that are worded the same way are more related than the items that are worded different ways. So within the red are the correlations between the items that have a positive, more, it means more forgiving, and the correlations in actually, those are the reverse coded items, excuse me. The correlations in blue are the ones that are more is more forgiving. The correlations in red, where more means less forgiving. But point being, there's going to be 2 traits here. Like I can see it in the correlations, and I'll show you how these problems manifest themselves in the results of the factor analysis as well. Um, if you know what the means and the variances are of your variables, then that paired with the correlations all that you need to reproduce the observed covariance matrix. So as part of your due diligence in reporting the results from these types of analyses, you want to provide the means, variances, and correlations of your indicators because then people can compute the covariance matrix that goes with the model that is part of the model. Basically, this is what the model is trying to operate on. In this case, we have complete data. The actual covariance matrix is not going to be computable if you don't. I'll show you a way to estimate that as part of the modeling process. But this is useful for descriptive purposes because then anyone can take this matrix and try to do their own analyses of your data. So that's one of the nice things about CFA is that means variances and covariances are sufficient statistics. You don't need the raw data to be able to reanalyze the data. So either correlation or covariance, and just to remind you how to get back and forth, here's the formula for covariance given correlation, and here's the formula for correlation given covariance. So you just need one or the other along with the means and variances of the variables. So first question, what kind of indicators is CFA supposed to be for? What kind of observed variables is this type of factor model designed for? Normal, continuous, yes. Symmetric and continuous. I have never seen indicators that actually meet that. But here's what we got for these. So these are histograms of the 1 to 7 ordinal response format that we're working with. Do these look normal enough to you? Well, they're not. No, the answer is no. Probably not. How implausible a linear model of a factor predicting these responses is going to be is something that we're going to investigate as part of the process, but be skeptical. Solutions for non-normality include just changing your type of estimation to be robust, where there's corrections built in that are going to adjust the fit statistics and standard errors, versus just finding a whole new model. For ordinal data, arguably in most cases, we want to have a new model. Do you know why I fit a normal CFA model to these data instead of an ordinal CFA model? Do you want to know why I did that in the year 2001? I didn't know any better. That is correct. That's why. Would I do it differently now? Absolutely. But hindsight is 2020. So yeah, this is the best that I knew how to do at the time. I have a whole list of publications, by the way, we could go through, and I can point out all the things that are wrong with them that were the best I knew how to do at the time that I now know better. It happens. It will be okay. Question. When you are measuring one latent trait, can there be multiple factors within that trait? Yes. So a lot of times people will conceptualize sort of a general trait, such as forgiveness, right? This is the Heartland forgiveness scale. But the way that they decided to measure this general trait is with more specific sub-traits, or like traitlets, kind of like sections of a trait, self, other, and situation. So the hypothesized factor structure here is that 6 of the items measure self, 6 of them measure other, 6 of them measure situation, and that those 3 factors then, the pattern of correlation among them would be consistent with what's known as a higher order or second order factor, like the big forgiveness. So that's where this model is eventually heading, is the idea that there's big forgiveness, which is in turn measured by self-other situation, which is in turn measured by the actual items. So it's like a layering of factor models. But in order for the big one to be right, each of the submodels has to be right. And so an important first step, even if you think overall you're trying to end up at one place, is to make sure that the sub-dimensions are following the expected factor structure. Because I got to find out if these 6 items measure one thing before then I can look at how that one thing relates to other traits within the model. So, good question. Is it normal enough? It's not the worst I've ever seen. But this is an example, though, by the way, of rules that people may tell you that are not to be followed. So you will see things like, oh, if you have at least 5 choices, that's normal enough. Has anyone ever tried to tell you that? You'll read this in published literature, that if you have 5 options, you can treat it as normal. No, because it's not just how many options you have. Look at item 6, the bottom right-hand corner. That's not normal. And if you gave them 9 options, it would still not be normal, because that's an item that everybody is agreeing to. Everyone is picking either a 6 or a 5, 6, or a 7. So it's skewed. And so what's going to happen is that a linear factor model is going to predict responses that are going to go out of bounds. The line, sorry, this way for you guys, the line is going to want to predict a score of 8, 9, 10, but you can't have that. So it's not just the number of choices, it's whether or not they're symmetric in their distribution. If you see skewness like this, that's a giveaway that a linear factor model is probably not going to work. But I want to show it to you because this is the simplest factor model that we'll see this semester. We're going to make it harder and more complicated and more employable. Just think of it that way. Okay, are we ready to do this? Okay, questions before we dive in? All right, let's dive in. So M+, the header information to read in the data, tell it the names of your variables and all that good stuff. We only have to do that one time. So this code is going to be used in all of the following models. Question before we get to, if our indicators are ordinal or nominal, can we just use robust errors? Ordinal, maybe. Nominal, no. If you have a nominal indicator, then fitting a line through your choices makes no sense because they're not ordered. So there's no way to say like which way the line should go. Robust standard errors are a good strategy when you don't have another model that's readily available that would map onto the type of distribution. I'll show you some examples of that later in this lecture, but for ordinal data, there is a model that's designed exactly for that. And so arguably, that would be a better choice than pretending that it's normal and continuous. Okay, so M+ commands are relatively straightforward. The things in blue are the only parts that are dedicated like sections of the code that have colons after them, and otherwise all of these commands in here end in semicolons. So if you're used to programming in Sass, this is all going to look just fine. Comments in M+, the green right here, begin with exclamation points. And you can put them at the beginning of a line or anywhere in the line, and it stops reading after you hit the exclamation point. So I have exclamation point comments all over the place to tell you what each of these commands do. First off, as a title, that's optional. That's if you want something that shows up in your output file as to what you're doing. The data file. So I did a video about this, but just in case that's been a while or you didn't get a chance to see it, M+ can only take text format data. You cannot read in data from R, Stata, Sass, SPSS, etc. You have to convert it to a text format. It can be a .dat or .csv extension. I recommend the latter, comma separated values, CSV, because if you have a file with a CSV extension, you can double click on it and it opens in Excel. That's why. That way you can look at it and make sure that it looks okay. Every package, stats package, including Excel, has a way of generating a comma separated values version of the data set. And inside the M+ guide that I gave you as part of the example files, and it's also linked from the course website, there is code to do so within Sass, Stata, and SPSS. And I'm sure folks can figure out how to do it in R if they haven't already. Another question about errors, I think. When data is not normal, we can't use these models. Can we translate the data to the normal distribution? You can do transformations to make the data, I wouldn't say more normal, but to make the linear model more plausible. I do have a couple slides on that coming up, but I would still say that is less preferable than fitting a model that is readily designed for the response format that you have. If you have ordinal data, there is a kind of model for that. It just takes what you're doing in CFA and it adds a couple other layers of complexity, which is why I can't start there, but we will get there this semester. Okay. In terms of the placement, if you just put your CSV file in the same folder as your input file, so the thing that you are typing all of this stuff into is a text document that ends in a .inp extension for input. If those are in the same place, then you don't have to provide any file location information here. So that is what I recommend. Otherwise, you have to list the path. So it'd be like C:/folder/folder/folder/. And if you go past 90 characters, you will run into problems because this input file only reads 90 characters across. So if your file name is so long that it goes past 90 characters, then you're going to run into problems. So the easiest thing to do is just to make sure that your input and your data are stored in the same place. Because CSV files tend to be very small, it's pretty easy to do. So that is what I'm going to recommend and assume that you have done. So we're using a file called example4. These two next commands are defaults, but I've included them here just in case you want to change them. The type of format, it's either free or fixed. Fixed format data is when you have to tell it like column 1 and 2 is this variable, column 3 and 4 is this variable. It's a pain in the ass. Don't do it unless you absolutely have to, and I don't know why you'd have to. So we'll stick with free format data. And then type equals individual is when you have one person in each row. So the format of these data is such that each person is a row and it's like indicator 1 is a column, indicator 2 is a column, all of the different variables go across in the columns. This is in contrast to how this would be set up to do these same sorts of analyses in other programs like SAS, in which each item would have to be a row. In this case, it's each person is a row. So this is what's known as wide format data or multivariate data. It's the usual way that people store data, I would say, in the social sciences. The alternative is that you can read in matrix data. So if you only have a covariance matrix as your data file, like from a published article that you wanted to play with, you can read in the covariance matrix instead. It doesn't have to be individual. So this part then just tells you what data file it is and the format. So any questions so far? All right, names. Okay, attention, attention, attention. I'm waving to get everybody's attention back. Are you with me? Okay, this is the thing that people screw up. Does the blue text stay the same? Yes. So that the part that's in blue, you have to type exactly. M plus is not case sensitive though, so you can type it however you want. My general preference when I'm typing code is that dedicated commands I type in capital letters, and options like variable names that I would change are usually in title case or lowercase. But names, it requires you to input a data set that has no names in the first row. I guarantee at least some of you are going to accidentally do this because I do this all the time myself. When you export your data into a CSV format, the default is almost always that the names go into the first row of the spreadsheet. You have to take them out. MPlus does not have the names as part of the data. The names of the columns go here instead. If you have the names, you will get an error message that says, I don't know what to do with this. There's words here. Question, if there are blanks in the data. I will get to that in just one moment. So the names, you have to list every single variable that is in your data set in order. Oh my God, so if you have a large file with lots of covariates, you have lots of names, correct. So I would encourage you to cut your data set down to just what you need. Just the things that you would need for a particular analysis or set of analysis to save yourself the headache of typing 7,000 variable names. The other problem with this is that each of these names can only be 8 characters or fewer, which makes it even harder to differentiate all of your names. So because the variable names are not tied to the data anymore, you can name them whatever you want. It doesn't know what they used to be called. So you can rename your variables to stay within that convention of 8 characters or fewer, but then the more variables you have, the harder it's going to be to tell them apart. So I would highly recommend cutting your data set down to as few variables as possible in order to use the software. Are you saying that we should take the names out, cut and paste into the name spot? Yes, that would be fine. Otherwise, if you have a listing of names that your software can generate for you, then that would be one way to make sure that you don't accidentally forget them or mess around with the order. But yeah, they have to be in the same order as the data set. And you can just pick whatever variables you need for an analysis. So the use variable down here then subsets exactly to what you need in that particular model. So you notice that I have a lot more variables here. I have all 18 of the items, self 1 through 6, other 1 through 6, situation 1 through 6. I have the subscales and I have the total score already computed. I have all of that information in the data file. For this particular model, the series of models I'm going to show you, I'm only using the 6 from the situation subscale. So use variables allows you to subset your variables and not include all of them. There is also a use observations option that works like a filter that allows you to subset people. So just as an FYI. The M plus guide that I made has a bunch of the extra things that are not necessarily going to be part of this, but that come in handy whenever you're doing analyses. Use observations is another one that comes in handy a lot of the time. Okay, so with me so far on this. Okay, questions coming in. Let me catch up here. Would you import all the variables in the names commands if you would just use those specific ones? In a project, you may know that eventually you want to use a certain set of variables, but you're not there yet. So in this case, where I'm going to eventually get to is a model that has all 18 items simultaneously. So knowing that, I'm going to keep all 18 items in the data file as indicated by the names statement, but this particular analysis that I'm going to demonstrate is only going to be using the 6 situation items from that subscale. The CSV file and the M plus zip file, yes. Inside the example files in the video that I used to demonstrate M plus, I showed how to take an Excel file and compute a CSV file from it. In the example files that go with this example 4, you do not have the data because it's real data and I can't give it to you. But what I did give you is the input file that generated all of these things, as well as the individual full output files of all of the analyses. So I can't give you the data to play with, unfortunately, but yeah, I can't. That's the end of that sentence, I think. All right. Other questions before I go to the next one? I think I hit all the questions in the chat window. Send it again if I missed one. We're going to talk about missing data as the next thing here. Missing data. So you are allowed to have missing data that are indicated by just a dot. Don't do that to yourself. I have had more problems with it reading files incorrectly when missing data were in fixed format with blanks or just had a dot, because you end up with dots elsewhere in the file because of decimals, and I've had instances in which it gets all screwed up. So I am very superstitious about this. I always fill in my missing values with some sort of missing value indicator. I have chosen 99,999 in this case. You could pick whatever you want, but this is a step that I do ahead of time just to make sure that the data read in correctly. The problem with this data process is that, so M+, like this code, is like 1985. Maybe some of you weren't alive then, but just trust me, this is like 1985 level of programming. And the output looks like that because they've put all of their efforts into actually developing the models. They come up with updates of the program several times a year, and they always have the newest and coolest shit in there. And so they don't have time to work with like the data functional part. So there's no point in this process where you can import your data into M+ and like click on something and see the data file pop up. There's no data interface. So you have to do detective work to make sure that it's actually read your data correctly, because you can't verify it any way other than running things and seeing if they look right to you. Does the CSV have to have them as the 999, or does the CSV have blanks? You have to change them from dots or blanks to the 9999. You have to do that inside your software package. I have examples of how to do that I can send if anyone needs that, but that's part of the process of getting the data ready, is to fill in the missing values. It can run with dots, but I've just had too many problems with that, so I don't ever try anymore. Okay, did that help? CSV missing data? Okay. But if the missing command, does that change them? No, this means that it's already in there and it's just going to recognize them as missing. So anytime it comes across that value, it's going to read it as a missing data. It's not going to change it. Yes. You can have more than one, and you can say like some variables it's this number, but other variables it's a different number. That gets confusing, and so just keeping them all the same is probably the easiest way to make sure that it words it correctly. All right, and then this option for ID makes it so that if you have an ID variable, that it will be part of any outputted data set. That way you can merge things back together again. So that's something that's helpful to include. All right, So this part up to here, title, data, or just really data and variable, that's just making sure that you have your data in and that it understands what the contents are. That's all we've done so far. For analysis, this is where you're going to have options for what type of analysis and estimation you want to choose. There are a few different types. Type equals general is what we're going to use most of the time in this class. And estimator refers to the type of estimation method. The MLR stands for robust maximum likelihood. That's what we're going to use in this class for all analyses for data that are supposed to be normal, because it offers some degree of protection against multivariate non-normality. It also reduces to regular flavor ML when if you don't actually need the correction. We haven't talked about estimation yet, that's coming next, but just so you know that this is how you would specify what you want. M+ does come with defaults for all the situations, and so if you don't put anything, it will make some kind of decision for you. But this is what we're going to use for the CFA models in this class. More questions. Let's see. I thought only factors and residuals follow multivariate normality. So question about what has to be normal. Strictly speaking, we are assuming that all of the factors have a multivariate normal distribution. So if there's, in this first model, there's only going to be one factor, so it's just univariate normal. When there's more than one, it's multivariate normal. That is not something that you can change easily. That's sort of like a given in almost all analyses of this type, is that we're saying the factors are normally distributed. There's some research that suggests that if they're not, it's not as big a deal as other types of violations. In terms of the indicators, in this case, because the only thing that's predicting them is something that's normal, saying that the indicator residuals are supposed to be normal is the same thing as saying that the indicators themselves are normal. Because we have just two pieces of a normal, residuals and factor, that come back together again, that combination has to be normally distributed as well. So this is the one case in which I'm saying the data have to be normal, not just the residuals. It works out to be the same thing in this instance because the factors have to be normal. If the ID includes letters, is that okay? No. M+ does not do well with text variables. They may say that's okay, but that's another instance in which I found problems. I get rid of anything that looks like a date or a string before I go through this process. And make sense about the normals. Yeah, we'll talk more about what's normal and non-normal in the context of estimation, but in this case, it does work out that the indicators themselves are assumed to be multivariate normal. Indeed. Okay, other questions? All right, save data. If you want to save stuff like factor scores, this is where you can tell it to do so. You don't have to, but I'm going to use it to do some illustrations later on. To make pictures of distributions of things, that's the plot option. There's three kinds, and I just usually ask for all three. That way I don't have to remember which each kind gives me, because asking for more doesn't hurt anything. And then output. This is where you can ask for extra stuff that is not necessarily given by default. Mod indices. We haven't talked about what these are yet, but I will come to call them voodoo. That helps you improve your model fit. This is the model, the software trying to help you decide what should be in your model. So you should always be very careful to pay attention to those, but those are pieces of information that we're going to use to diagnose misfit coming in. Standardized solution. So to rephrase the factor model equations into a standardized version where everything is in a metric of correlation, we will ask for that. And then these other things have to do with diagnosing misfit, which we haven't talked about yet, as well as the extent to which the factor scores are representative of the latent factor if you actually were to try and estimate their value for each person. So we haven't talked about most of this stuff yet, but it's stuff that we're getting to eventually. Okay, so any questions on the setup of just getting the data file in and setting options for stuff thus far? What is the 6.635? Good question. That is the cutoff value for printing suggestions to make the model fit better. That corresponds to a suggestion that would improve the model at p less than 0.01 for 1 degree of freedom. Something we haven't talked about yet, but that's where that number comes from. It's a chi-square critical value. Other questions. So do you just run title through output one time and you can swap out the model, or do you have to redo it? So each of the M+ input files, you don't run like a section of it at a time, you run the whole thing. So what's going to end up happening is, let me show you what I have for background here. We'll go into my files where we actually have all the data. I think, actually, no, I take that back. I don't have it. Inside example 4 for the HFS. So I have, this is available to you, all of the individual output files. Each time you run it, you run the whole thing. So the first model that we're going to look at, for instance, right here, let me go find it. It was on my other monitor. 1 second. There we go. So the output files that we're going to have, it spits back all of this stuff to start with that we just went over for the input process. And then everything that has to do with the particular model that you're running goes under this section model. But each output file is like one thing. So it's one input file and one output file per model. The way to get around that so that you can have more than one model in the same physical file, because otherwise it gets to be really overwhelming, is to have all of them in the same file, but comment out the ones that you're currently not using. So let me show you what this looks like. So here's model 1 that I'm going to run. Model 2, model 3, and all the other ones are in here, but they have exclamation points in front of all of them to temporarily shut them off. So you can turn on and off models from the same file, but each time you do a run, it generates a separate output file that is saved to your local disk with an OUT extension. Okay, long answer to a short question. Does that help? Okay, so yeah, you'll have, the way that I generally do this is I have maybe one input or one input for a type of model and then like separate outputs for each model that's contained within that. So I gave you guys this input script that has everything in one place, and then I also gave you the output file from each of the runs so that you could see what unique output was generated by each of the model codes. Okay. All right, are we ready to look at the code, do some modeling? Keep the questions up, I appreciate that. Knowing how to do it in practice is the goal. So all the factor analysis model parameters I have referred to in my code so that you have a listing of everything that you are asking it to give you. This is overkill, meaning that you don't actually have to type all of this. The people who made M+ hate typing, and they have put together all kinds of default things that happen to save you from having to do typing. The problem with just relying on the defaults is that you don't necessarily know what you're asking it to do because so much of it is left unstated. And they may change what the default is between versions, and so the same code does something different. So to be completely transparent, completely reproducible, I write out everything that I'm asking for in the model, even the stuff that I don't have to write. That way you know what you're looking at. So what we're talking about in this context, a factor model, there are 3 different types of parameters that we're going to be dealing with initially in the measurement model, right? Measurement model is item things. So each item is going to get an intercept, it's going to get a factor loading, and it's going to get an error variance. We also need to be able to tell it which items go on which factor, and then to specify the metric of each factor, because each factor needs a mean and a variance. And if there's more than one factor, we have to decide whether or not we want to have them to have a covariance. Well, this model is a single factor model. that's where I'm starting, because when they made this scale, they thought that these 6 items were all supposed to measure one construct, which is forgiveness of situations, the extent to which you are capable of forgiving situations dealing with things that happen to you that are no one's fault. So the first thing that I need to do is to define my factor and tell it which indicators are going to be measures of it. So I am creating a name for my factor. Like all variable names in M+, it can only have 8 characters or fewer, and that's why the name of my factor is going to be sit and not situation. So when you are doing this on data you care about, don't name your factor sit, right? Name it whatever you're talking about in terms of your data, right? Name it intelligence, name it depression, name it anxiety, name it whatever the trait is. That will help you understand your output better. It's sit for me because I'm measuring forgiveness of situations. Magical word by. There are very few words in M+ that you need in order to convey the structure of your model. By, on, and with. There's really only 3. By means measured by. How is my latent variable being measured? It is measured by these things. These are my indicators. So I am listing out the 6 items that I included at the top in terms of which variables are being used in the model. So these are my 6. And they are showing up right here. And for the sake of being able to follow what's going to happen, I kept the R at the end of the number to indicate which ones were reverse coded. They've all been reverse coded already, such that more forgiveness is supposed to be indicated by higher scores. So they all should be positively correlated at this point. The star. The star is also not necessary. I'm trying to be explicit. The star refers to the factor loading that relates each of these observed variables to the latent factor named sit. The fact that each of them has a star means that I'm estimating each individual indicator's factor loading separately. So each gets its own loading, the lambda slope for how the predictor trait is predicting the observed variables as the outcomes. And just like every other command, semicolon at the end of the line. Semicolons are important. As I indicated in the note above, if you wanted to fix a loading, instead of having a star, it would be an at sign above the 2 on your keyboard, the email at, and the number that you want to fix it at. So we'll see an example of that in the next model. So what I have done in this one line of code is tell M+, hey, I have a new latent variable. I'm going to call it sit. That latent variable is going to be measured by 6 indicators, and this is what they are. Each of them is to get its own estimated factor loading, relating the trait as the predictor to the item as the outcome. Okay, so how many DVs, dependent measures, do I have in this model? Is it 1 or 6? This should be a hand question. 1 or 6? How many DVs? Outcomes. Got 1 vote for 1. No one else is weighing in. 6 question mark? Yeah, it is 6. The variables that are in your data set are the outcomes. The latent factor is the predictor. The predictor we don't have. It's latent. It's pretend. 6 outcomes. 1 trait. That's what I've got right now. So of the 3 measurement model parameters, intercepts, factor loadings, error variances, this first line takes care of the factor loadings. That's the most important part. Next line, intercepts. Variable names that you type inside brackets are either going to be means or intercepts depending on the context of the rest of the model. If the variable in question is treated as a DV, as an outcome, then it gets an intercept because it gets the expected outcome value when all the predictors are 0. If the variable in question is an IV, is a predictor, then it gets a mean because a mean is unconditional. It knows which it is based on the context of what you're doing. This is an example of a line that you don't have to type. By default, all outcome variables get estimated intercepts. And it is rarely the case that you would change this, that the estimated intercepts are allowed to be separate for each different outcome. Each one gets its own. Question, what is it doing with the means or intercepts following this code? Just providing estimates? Yes. This code is saying, hey, go find this, please. Add this to the list of numbers that I'd like you to find. And I say find as opposed to calculate because we're going to be talking about how this process works is through likelihood estimation, where there is an iterative search that happens to try and decide what the most likely value is of each of these parameters that we're asking it to estimate. So this list means, hey, go find me some intercepts, one for each of my variables, please, my outcome variables. Also, the third kind of measurement model parameter on our list, error variances. Outside of brackets, when you list a variable, you are either referring to its error variance, residual / error, or its variance. And it's the same idea of whether or not it's an IV or a DV. If the variable is an outcome, then what this refers to is its residual variance, its error variance, its leftover variance. If the variable is a predictor, what this refers to is its variance. All the variance there is to be had, not just the leftover part. So these are the error variances, and the stars after each are a way of saying that they are free, meaning free to be whatever they want. Please give me these as well. Okay. Other questions on the first 3 lines of the measurement model, factor loadings, intercepts, and error variances. The next 2 lines are important if you want your model to actually run and not blow up. Because we've talked about a latent factor named situation, but it doesn't have a metric yet. It doesn't have a scale. So we have to identify it. We have to give it a scale because it's an imaginary variable. And the method that I'm using to identify my latent factor in this model is to pretend that its scale is a z-score scale. So I am going to fix the latent factor's variance to 1, and I'm going to fix its latent mean to 0. So listing a variable by itself refers to its variance or its error variance. In this case, is this going to be variance or error variance? If I'm talking about the factor. One vote for variance. Another vote for variance? Yes, because the factor is the predictor. It's not being explained. So it's the factor's variance, like all the variance there is to be had in it. That's what's 1. Could I make this something else? Could I make it 10? Could I change the factor variance to 10? How about 100? Sure. The z-score scale is for convenience. The reason that a variance of 1 is useful is because then the standard deviation is 1. And if we think back to the interpretation of what a slope is, right? It's the change in y for a 1 unit change in x. What a unit is in this metric is a standard deviation. So you can think of for every standard deviation increase in the factor, the loading gives you the expected increase in the response. If you have a variance that's some other number, then you have to figure out what a unit is and it may be an extra step in terms of the interpretation that you don't want to have to do. So you can pick whatever number you want. 1 is a convenient choice for the context of the factor loading as a slope. Can I pick 0? Can I do at 0 for my factor variance? Because I just said I could pick any number I want, right? 1 vote for no, 2 votes, 3 votes. No, I can't. Yeah, I can't have a variable with no variance. We call those constants where I'm from, and constants can't relate to other things. So no, don't fix the factor variance to 0 by mistake. So this code right here and this code right here, out of brackets is a variance. That goes to 1. In the brackets is referring to its mean or its intercept. Mean in this case because the factor is a predictor, unconditional. So the mean is 0. And question, this is unstandardized solution. Setting the mean and the variance to 1 and 0 is still confusing. This is the unstandardized solution because we haven't standardized the outcomes. The outcomes are still on their original metric of 1 to 7. So they don't have standardized variance of 1 or a mean of 0 or any of that. So the factor itself isn't a standardized metric. The outcome is not. And that's what makes the solution on the whole unstandardized. The reason that we are giving the factor a mean and a variance is because it's an imaginary variable. We have to. We have to give it some way so that the rest of the parameter estimates can be found. And because there's only one factor, we don't have any potential for factor covariances, and we're done. And all of this code, you could actually just do this much and you'd get the same result. So I know some of you are familiar with the R program Lavaan. Lavaan has like a 2m plus like section to it because it ends up looking very similar. Like this boiled down version would be what you'd have to tell Lavaan. In this case, you tell it the factor variance is 1, factor means are 0 by default, indicator intercepts are all estimated by default, indicator error variances are all estimated by default, and this star right here is necessary because by default also it fixes the first factor loading to 1. To override that specification so that you can fix the factor variance to 1 instead, you have to say, no, don't fix the first loading, let it be whatever it wants to. Let it be a star. And the other ones are all estimated by default as well. Okay, other questions? If we do not designate them, do we have the default as we have learned? The default in M+ is to estimate factor variances, fix the factor mean to 0, estimate the loadings of all the indicators except the first one. That's what the default is. We're going to see that version of the model next. And no, I don't expect you to memorize the defaults. So it won't just move and have the default to the next one without a star. No, it will not. It's not smart enough to do that. If you star the first one, it's like, okay, my work here is done. Everything else is going to be estimated. All right. Questions on this? So we've set up a factor model. We are saying that the reason these 6 indicators are correlated is because they all measure the same thing. What that thing is a question of validity. That's a different class, but the same thing. I'm naming that thing situation. I could name that thing Sesame Street, right? Like the interpretation of the items is not what we're talking about here. This is my theory of situation that these items are supposed to be measuring. I am allowing the items to measure the latent trait differentially well because differentially well is what's implied by allowing each item to have a different factor loading. You can have an item that's a better item than another because its factor loading is higher. These are unstandardized factor loadings, and so they're going to be in the metric of the variable. So that's one of the reasons why we'll look at the standardized solution to put them into a correlation metric where they're all on the same scale. Then we can compare across them to see which is the better item, correcting for differences in variance. Okay, are you ready to see some outputs? Survey says, all right, so this output has more words in it than what you're going to see. This is like the Proc Lisa version where there's extra notes here. So if your output does not have labels on it, that's because I'm trying to be nice. Your tuition dollars at work. So this, for instance, I added this because all it tells you for this section is sit by and estimate standard error and across the top. So all of these parameters are somewhat labeled, but not greatly labeled. But across the top of the columns, the first column is the estimate of the parameter, the end result of the iterative search process for what value of the parameter would result in the highest combined likelihood of the data. We will talk about likelihood in more detail next time, but basically the number that works the best to make everybody's data the tallest possible altogether. Standard error for that estimate, which is a byproduct of the estimation. It's related to the second derivatives of the likelihood function with respect to that parameter. It means the thing that it usually means. So a standard error for a statistic is how far off, on average, the statistic would be from the population version. It's an index of inconsistency or expected wiggle across samples of the same type. In these models, we would generally not care so much about the test statistic, but it is provided for you. So estimate over standard error. What do you guys know that as? It's a letter, one of two letters. We'll see if you get it. One vote for T, that's one of them. Z/T, Z, F is squared. Yeah, so whether it's T or Z depends on whether or not you are paying attention to sample size. So estimate over standard error, that idea more generally is known as a Wald test. And if you are treating that ratio of estimate over standard error as a T, then you need denominator degrees of freedom based on your sample size to figure out what the reference critical value is. Do you see denominator degrees of freedom anywhere on this page? Nope. M plus is like, yeah, homie, don't play that. No denominator degrees of freedom. So that thing is a Z. That thing is a Z to M plus, which means this is the p-value that goes with that Z. So for instance, a Z of 17 means that if the null hypothesis of a zero loading is true, then my loading of 1.2 is 17 standard errors away from that null, so we would call that significant. Significance is not really a thing in these models. It takes very little for a factor loading to be significant. We really want to pay attention to effect size here. For the other letters, thank you for participating in the quiz, folks. If you have a 1 degree of freedom test, so you're testing one thing at a time, T squared becomes F. If you're testing one thing at a time without denominator degrees of freedom, Z squared is chi-square. So all the stuff that we're going to see in M plus is going to be Z's and chi-squares because we don't have denominator degrees of freedom. And that is, I want to say, universally the case. SEM software doesn't do denominator degrees of freedom, even though arguably it probably should. And it also doesn't do residual maximum likelihood as a small sample approach. So these are sort of large sample uses of statistics. Okay, so what are we looking at here? These are the loadings. So the first column is the estimate of the factor loading, then it's standard error. So all of these have numbers here because the way that we identified the model is by fixing the factor variance to 1 so that each item could have its own loading. So these are in the metrics of the original variables. These are slopes. So for instance, the first loading of 1.234, and I swear this is real data, that's just a coincidence that that's the number, 1.234. Sounds like the password to Huey's iPad, by the way. It was very funny. He was trying to tell his big sister about his password. He's like, it's a secret number that no one else can know, okay? It's 1, 2, 3, 4. And he's dead serious, right? So I hope none of you want to break into Huey's world and steal any of his Minecraft games, because that's what the password is protecting right now, is his ability to FaceTime with his family and play Minecraft. But anyhow, 1.234. That thing is a slope. So slope is the change in y for a 1 unit change in x, right? So y in this case is the response to item 1. X is the latent trait of situation forgiveness. So for every unit increase in the trait, so every standard deviation higher in the trait, your expected score on this 7-point item goes up by 1.2. That's what that number means. In contrast, for item 2, your expected score to item 2 only goes up by 0.7 for a 1 unit change in the factor. Now, I really want to look at these numbers and be like, okay, does that mean that item 2 is not as good as item 1? But I can't really say that because they are not on the same scale. Even though they're both 7-point items, they have the same potential scale. Differences in the actual variance of each item is going to mean that those slopes are metric specific to the outcome. So they're not comparable yet, but we're going to get there. Question, so how well the items represent the factor? Yes, it is, but we can't compare across them yet because they're unstandardized. They're in the units of each individual outcome, and each outcome has a different variance, and therefore what a unit is slightly different across outcomes, even though they all have the same 1 to 7 format. But eyeballing it, it sort of looks like the ones that have the R's are relatively better than the ones that don't. We'll see from the standardized solution if that pattern continues to hold true after adjusting for differences in variance across the items. Okay. Next one listed is the means, and in this case, the only thing that has a mean is the latent factor, which is given right here. And question, why wouldn't we always want to use the standardized solution? If our objective is to look across the items and see which one is relatively better, we want the standardized solution. If our objective is to look across the items and compare how they behave across groups or occasions, alternative samples, some kind of comparison like that, we want to stay in the metric of the unstandardized loadings. So each type of solution is useful for a different potential purpose. This version of the solution, where we have the unstandardized factor loadings, is designed to recreate the covariance matrix across the items. When we get to the standardized solution, in which these regressions are phrased as correlations, their job is to create the item correlation matrix instead of covariance matrix. So it's the same information, just whether or not you're correcting for differences in unit is the difference between the solutions. This is the regression unstandardized solution in the metric of the original variables that we're looking at right there. Although the scale is the same, it is not comparable. Yes. So all of these items are measured on a 7-point scale. So in theory, they're comparable. But if you look at the actual differences in variance, here's the variances across the items. The items that are reverse coded have more variability. So when talking about what change in y happens for a 1-unit change in x, you can't exactly say that it's the same effect because y is more stretched out for some items than others. So they're as close to comparable as you can get without standardizing, but the goal of the standardized solution is to make sure that they're completely comparable with respect to the same standard deviation on the outcome side. Right now we have the same standard deviation on the factor, but not the outcome. Okay, lots of questions on standardization. Does that help? Okay. Then back to the output. After the loadings, comes the mean. Now let's look at these numbers. Estimate of 0, standard error of 0, and a z-value of 999. Are those numbers? No. This is not a z of 999. This means because we fixed the factor mean as part of the identification. So it doesn't have a standard error because it wasn't found. We said make it 0. Now go find everything else around it. And so M+ prints this 999 whenever it can't come up with a test statistic because the thing hasn't been estimated. So it's not a real 999. It's just like an indicator that just keep on moving. Intercepts of outcome variables, such as the items here. In this method of identification, these are actually the item means. Whenever your factor mean is set to 0, the item intercepts are the item means. The term intercept is still more appropriate because this is conditional on the definition of the factor and its scale. The intercept is the expected outcome when the predictors are 0. So because the factor has a mean of 0, these are the expected outcomes for the average person. Expected value, these are the means of the items. And we would also disregard all of these test statistics because they are telling us that these factor means are not 0, which is not something that is useful to know in this context. Variances, in this case we have the variance of the factor. The 999 show up again because it is 1 because we set it that way for identification. So it doesn't have a standard error because it wasn't found. Last but not least, the residual variances. These are the item error variances. So these are the variances that are left over after controlling for the factor. So we talked about dinosaurs last time briefly. We have factor variance. This is the not the factor. You can call it unique variance or specific variance or error variance. I don't care. It's not the factor. What it is, not the factor. And so these are variance estimates, standard errors, and so forth. So I can write out some of the model predictions using this information. For instance, if we focus on item 1, here's the model that predicts what item 1 should be. Its intercept was estimated at 4.547. That was the value that was found right here. The factor loading for item 1 was estimated at 1.234. That's found up here in the loading section. And note that in the individual equation, there's E here. The idea that, and that should have an S on it actually. Let me fix that while I'm in here. That each subject has their own error for item 1. But we don't put the error variance in there because this number right here refers to the variability across people in the errors. It doesn't refer to the error for any one person. So that doesn't go in here. Where this residual variance goes is in trying to get back to what the model says the original variance of item 1 is supposed to be. The original variance of item 1 is part factor and part error. The part that's due to the factor is given by the loading squared, the variance of the factor, which we set to 1 for identification, and then this is where the residual variance shows up as the remainder. So because each item gets its own residual variance, the original item variance is always going to match. Because whatever part factor doesn't get, that number is free to vary to plug the hole to get back to the original item variance. So whatever factor doesn't have, not the factor swoops in and picks it up. So the original variance of item 1 is 3.049. It's perfectly recreated because of this room to maneuver, that each item getting its own error variance that's what's accomplished. The predicted covariance across items is also given from this solution. So for instance, if I looked at what the model says the covariance should be between items 1 and 2, the model says it should be the loading for item 1 times the variance of the factor times the loading for item 2. Well, if I plug in those values, the model says the covariance between items 1 and 2 is supposed to be 0.866. But in reality, the covariance from the data is only 0.577. So we missed. Now, is that close enough? I don't know. I can't do it. I can't tell from eyeballing. But what we're going to do is ask it to look across all of the covariances and compare how far off each one is. What is the discrepancy in correlation across all the covariances, excuse me. And that's going to form the basis of model fit, the mismatch between what the model says and what the data say. So we'll have to look at that before we'll have a sense as to whether or not the solution is worth believing in, whether or not the data are consistent with the pattern of correlation that would be created from a single factor. Here's the standardized solution. And the difference is that in addition to having the standardized factor, mean 0, variance 1, now this is all the items are standardized to mean 0, variance 1, 2. So the loadings are in correlation metrics. Now I can compare across these and say which items are relatively better. And I would say items 1 and 3 look the best, and the others are a little bit further behind. So the correlation of item 1 with the factor is 0.7. If I take that correlation, R, and square it, that creates the R-square values that are given at the bottom. So those are your effect sizes. So if I think of this correlation as R, if I square that value, that shows up as R-square. This tells me what proportion of each item's variance is due to the factor. So for item 1, it's half and half. That's not bad. I'll take that. Item 2, only 26% due to the factor. It's not great. So I'm not going to pay attention to significance. I'm going to pay attention to these in talking about how good each item is, how much variance is attributable to the factor. The idea of reliability creeping back in here. All right, questions on any of that since we're just about out of time? All right, well, we haven't talked about fit yet, so we don't know if we can trust these values yet. The bottom line is that until the model fits, we can't really interpret them too well. So we'll head in that direction next time. So office hours start now. Let me know if you need anything. Otherwise, stay safe and sane, and I'll see you Thursday. Bye, everybody.
I have a quick question.
Yeah.
For like our homeworks and the project we're doing with our real data, i.e. the assignment we just turned in, I was planning to use some real data that I actually have from my undergrad, which you know about. And